In this video, we're going to briefly look at static electricity for GCSE science. Now, at GCSE, it's a triple topic, but at Key Stage 3, it is generally taught to everyone. So the most common thing that we always talk about when we talk about static electricity is the classic Van de Graaff generator. And this is a really nice place to start explaining what we mean by static electricity. So in a Van de Graaff generator, we have a rubber belt that moves round and it's attached to a metal dome. And we have a little brush that is attached to the metal dome and touches the rubber belt. And that creates friction, which causes electrons to transfer from one material to another. Now, in a Van de Graaff generator, the dome actually gets positive and the belt gets negative. Now, the bottom of the belt is earthed to ground, so the negative charges end up flowing down here, and we end up with a difference in charge. Now, because the rubber is an insulator, we don't have charges flowing back up. And I'm going to put equalize because the charges won't conduct along the rubber. So now we have a positive charge separated from ground. And because the air is an insulator, because the rubber is an insulator, we don't have a flow of charge. If we were to put a wire here and connect it with ground or connect it to the earth, then we would complete the circuit, current would flow, and we would have current electricity. But we don't, we have static electricity. So what does this mean? Well, it basically means we have a build-up of charge. And if we have a build-up of charge, then we have a force. And we know that opposite charges will attract, and if we have positive charges, they will repel, and if we had two negative charges, they will also repel. Now at GCSE, we have for triple, we have to go a bit further. Students have to be able to actually draw the force lines that represent the electric field. So for a single charge, the force lines are really simple. They are uniform like this, and the arrows go away from the positive charge. The arrows go in the direction a positive charge would go. So if it's a positive charge, the positive will be repelled, and if it's a negative charge, then the positive charge will be attracted. So therefore the arrows go towards the charge. A couple of basic things. When we're drawing field lines, we shouldn't ever have gaps. That's bad because the field lines don't stop, the force doesn't stop. You should never have lines going into the same place. That's bad because why would a charge go this way compared to this way? The force is always, distinct at a given point, and we need to have them evenly spread out. So again, this kind of messy drawing is not acceptable. If we have more lines, then what does that mean? That means that the field is stronger. And if we have fewer lines, then it's a weaker field. If we were going to draw the field line between a positive and a negative charge, well, they feel a force of attraction. So what are the field lines going to do? It starts to look almost like a bar magnet. And again, we're doing the direction a positive charge will move. We could join those up if we wanted to. And then these ones over here will be slightly distorted. if it was a positive and positive charge, what would it look at? Or a negative and negative charge. So they repel, again, a bit like a bar magnet where there are two north poles together. It's going to look something like this here. And in the middle, there is no force at all because they cancel each other out. So if you've got a particularly interested and able class, you might want to go a bit further. You might want to talk about kind of non-uniform fields. So imagine you have a surface with a spike on. What happens? Well, when we have a spike, we have a stronger field. So the field here is spread out and weaker, and at the tip, it's much closer together and is going to look a lot more like this. And obviously we would put arrows on. So this is then nice because we can link it to something that students may well have observed. If students go on an AstroTurf, they will pick up charge and then they will get a static shock when they come off and touch a metal or touch their friend. If they want to avoid getting a static shock, what they can do is they can put their hand out and give somebody a high five. And what they're doing when they give someone a high five is spreading out all the charges. So the field is quite low and they won't get a shock. The electrons will just transfer. If they, however, point at somebody, the field becomes really strong and therefore there will be a spark and students will get a shock. This then links into the idea that everything will conduct, or anything will conduct, if the potential difference is high enough. So what do we really mean by potential difference? What we really mean in this context is the difference in energy between 2 points. So with our static example over here, there is a high potential up here because there are lots of charges. And there will obviously be some negative charges over here. There is a difference. Normally, atoms want to be neutral, so the charges want to balance out. So the more charges there are, the higher the potential will be. And if we get enough charges, if we get enough potential, enough energy, then they will flow, right? And we'll get a spark. And this just shows us that a conductor and insulator is really, relative. It just depends on the energy levels we're talking about. Lightning is obviously air conducting over a massive distance because the buildup of charge is so great. Something like plastic normally is an insulator because the typical potential differences, the voltages we're putting across it are quite low, so that we can't force the electrons to move. We can force the electrons to move in a metal, for example, because the electrons need very little energy to move. So when you get onto static, it actually starts to link in really nicely with current and the very idea of potential difference. Now, there are loads of nice demos that you can do with static electricity. We've obviously got the Van de Graaff generator. We've got simple things like a balloon sticking onto a wall. We've also got things like a balloon will bend water around it if we charge up the balloon by rubbing it, because it will influence the ions in the water. Or things like a balloon and a drinks can. You can attract or repel the can along a desk, again by charging it up. Or things like a plastic rod and some little scraps of paper. Again, we can charge up the rod and we can attract these scraps of paper. And these are all things that students can do themselves. What students do need to know for the exam with all these examples, they need to know the process, and the key bits is friction causing electrons to transfer. They also need to know a couple of specific examples, and you should always reference the exact specification about which way the electrons move. Do the electrons move from the balloon to the person, or from the nylon to the PVC, etc.? So there is a way that we can tell which way the electrons move. It's a bit like the reactivity series for electrons. It's called the triboelectric series, and this will tell us which way it moves. Students don't need to know much about this, but they always need to know a couple of specific examples depending on the exact spec. There's also a couple of nice demos online. FET, again, has some really nice demos for this, and I'll link to those in the description.